Good morning, everyone. Okay, so yesterday I have shown you three examples uh, on how we can obtain the capacitance of a three common configuration. So common configuration. One is the parallel plates. So the idea is just applying Gauss's law and then the potential. So once we apply Gauss's law to obtain the electric field, and then subsequently we use the obtained electric field to get the potential. So to relate the potential, which eventually will give us the capacitance. So for these three examples, the demonstration of Gauss's law have been shown. So the I think the complexity of the problem is not too difficult. Yeah. So the integration problems, the integration task, I don't think is too difficult here. Okay. So now, so we are going to look at, if let's say a parallel plates. So we have learned about parallel plates, uh, and we have also analyzed to get the capacitance. So now, if let's say two different dielectric, yeah. So earlier, there's only one dielectric earlier. So a single dielectric that is sandwiched between two parallel plates. So now, if let's say there are two different dielectrics between the two parallel plates, two different dielectrics, and each of the dielectric have a thickness of D1 and D2. The total added thickness is D. So in such configuration will provide us that, the equivalent circuit. The equivalent circuit in such way is a capacitor in series. So this is a capacitor in series. Yeah. So two parallel plates sandwich two different dielectric with permittivity epsilon 1 and epsilon 2. It is basically the equivalent circuit is two different capacitor connected in series. And how is that? So first, uh, okay. So let's say the first plate is positive Q. The charge distribution on over the plate is positive Q, and the bottom plate is negative Q. So let's say we assume this, and the two plates are connected to the positive Q with the positive terminal and negative Q with the negative terminal. So the overall potential is V naught. Yeah, the overall potential. That means the potential of this plate is V naught. Potential difference is V naught. Okay. And by looking at equation 1, so V naught is equals to the electric field at uh, permittivity, the electric field in region of permittivity mu1 in region 1. So let's say this is my region 1 and region 2. And also the electric field multiply the thickness in region 2. But if you see carefully, these two terms here basically represent the potential itself in region 1 and 2 respectively. Because bear in mind E uh, V is integration of ED, right? EDL, right? So I mean, since we reduce this problem here with only one dimension, I mean, it's a single dimensional problem. So the amplitude, I mean, the magnitude of the potential. Okay, the magnitude of the potential is E times D1 and E times D2. Yeah. So at the dielectric interface, so at this dielectric interface here, so at this dielectric interface, the one that I'm highlighting, so this is a dielectric interface. The boundary condition is the norm. There's no surface charge density, right? So so all the charge are on the plates. So the interface between the two dielectric does not contain any surface charge. So as a result of that, so if you apply the boundary condition, so in this way, uh, the normal component of the flux density must be equal to the normal component of the flux density of the other area. So D1n, that means this represents the flux density in region 1 is equals to the flux density in region 2. So this step here, by applying the boundary condition, the idea is to obtain the electric field in of E2 in terms of E1. So for this case, so again the plates is assumed to be infinite. The plates is assumed to be infinite uh, with respect to the distance. So with respect to the distance d, and with such condition, the electric field must be perpendicular to the plate. Okay, so we already knew that if you have a infinite plates, then the electric field is only in this direction. Yeah, coming from here to here and here to here. So 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 after obtaining the expression for the electric field in region 2, then substitute back. So substitute back in equation 1. Okay, so we have obtained, then eventually we need to do some algebra manipulation, and eventually we have relate E1 with the potential, as well as the the dimension of the plates. The dielectric thickness D1, dielectric thickness D2, and also the permittivity of the dielectric material. So if you look at if you look at the strategy steps, the steps that lead us to because we want to find out, we want to analyze how is it that two the two dielectrics sandwich between two parallel plates how can it becomes a two different, I mean, a capacitor connected in series? So we are going to analyze that. So now, I mean, now E1 is related to the potential V naught, and we know that the surface charge density, okay, at the dielectric conductor interface. So where is this dielectric conductor interface? So it is here. So it is this part here. Okay. Okay. So the dielectric conductor interface is referring to this plate and the dielectric of epsilon 1. So I mentioned already that this plate here uh, is positive charge Q. So following the two earlier, the earlier example in a few slides before that, basically we don't want to lose ge- uh, uh, the general discussion that we will assume every plates are charged with positive Q and negative Q. So the dielectric interface between the plates and the dielectric of epsilon 1. So the applying Gauss's law at this interface. So will give us a result that the surface charge density is equivalent to the electric flux density, and the electric flux density is related to epsilon 1 multiply the electric field. So we have established the relation between the electric field and V naught. Okay. So subsequently, so we have also established, that means now V naught is related to the surface charge density. So surface charge density is uh, charge over area, right? Charge over area. So this is basically, I can say Q over area. Yeah. Or S. Yeah. So from this, we can see that the capacitance is equals to Q divided by V naught, Q divided by V naught, and therefore is actually uh, Q divided by V naught is actually S D1 epsilon 1 plus D2 epsilon 2. Okay. So which is also equals to 1 over D1 epsilon 1 S, sorry, D1 divided by epsilon 1 S plus D2 divided by epsilon 1 S. So this can be easily seen as 1 over C, right? So 1 over C1 plus 1 over C2. Okay. So that's the capacitance. So therefore, uh, here if let's say, this analysis bring us to the conclusion that if let's say we sandwich the two plates with a different dielectric material, okay, it is equivalent to uh, two different capacitance that is connected in series. So, wow, now about, I mean, now we consider the dielectric material uh, interface in such a way that it is not stacked on top of one another, not like in this case. So this give us series. I mean, the if you compare the arrangement, if you compare the arrangement of the dielectric material, one is stacked on top of another. However, this is side by side. So the arrangement of the dielectric material, it is arranged in a way that is side by side. So this is seen. I mean, this is comparable to a capacitance connected in parallel. Okay. So the situation again here we have um, a material with permittivity mu1 and permittivity of mu2 that occupy an area of S1. Okay, so occupy an area of S1 for the dielectric material of epsilon 1 and occupy an area of S2. Okay, so similar we apply V naught, that means the potential difference between the two plates is V naught. So the potential difference between the two plates is V naught. Okay. However, because now, so the reason is because now the permittivity is different. So the charge density, on in the area S1 and the charge density on top of the area S2, that means at this interface here will be different, right? So the charge density between for this area S1 and also for S2, the charge density will be different. Okay, just due to the fact that because we have different permittivity and the charge density will be different, right? Okay, so for different dielectric material that occupy this area, so again the plates is assumed to be infinite, and the electric field here, I use a different, the electric field in dielectric permittivity of epsilon 1, it will be E1, and in area S2 will be E2. Okay. So the plates again, the overall the charge, the total charge on this plate is Q. Yeah. So the charge surface charge density for area S1 and area S2 added together is Q. Yeah, added together is Q. So here we see that the surface, the charge density on the plate that occupy area S1 is the surface charge density multiply area S1, which represent the charge on area S1 Q1, Q2 represent the charge that distribute over the area S2. So the total charge is Q1 plus Q2. While the surface charge density on the dielectric conductor interface, the surface charge density is related to, again, if you apply the boundary condition, the surface charge density is related to the flux density. So utilizing this relation here, utilizing the surface charge density relation in Q, in the total charge. So here we relate E1 uh, and epsilon 1 with Q now. So, but bear in mind the electric field is related, that I mean the electric field that for these two area is, it is equals to the potential divided by D, right? So substituting these two, I mean substituting for E1 and E2 into equation 1, we get, we relate directly, basically from here we can already see that this is epsilon 1 V naught over D times S1 and plus epsilon 2 V naught over D S2. So V naught is epsilon 1 S1 over D plus epsilon 2 S2 over D. Okay. So from here, so here we already see that the capacitance is in series. So the I mean the expression for epsilon 1 S1 over D is the capacitance expression, right? So it's the capacitance expression. And yeah, so if this for this configuration for the dielectric arrangement, the stacking one, I bring you back. So the stacking one is capacitor in series, connected in series. While if the arrangement is side by side, then it is a capacitor in parallel. Okay. So we'll go through one example. So evaluate the capacitance for the parallel plate capacitor, where the space between the parallel plates is filled with partially mica. So with permittivity of 6, assume the area of mica is 1/4 of the area. 1/4 of the area of the capacitor. So the total area is 10 cm square. The thickness is 2 mm. Okay. So obviously this area is mica. Okay. Obviously this area is mica. So by looking at the configuration of the dielectric, okay. So what would be the equivalent capacitance in this case, the equivalent circuit? So we have 1/4 of it, right? So what would be the equivalent circuit? Equivalent circuit for to represent this equivalent circuit, capacitance circuit that represent the arrangement of the dielectric. So one part of the area, you can see the two dielectric is stacking. So the other the what the unshaded region, it is the unshaded region we assume epsilon, yeah. The unshaded region is air, right? We assume permittivity of air. So the unshaded region, the permittivity is epsilon naught. So the shaded region is epsilon naught epsilon r equals to 6 epsilon. So it's given that the permittivity, relative permittivity is 6. So therefore, the permittivity of the material is 6 epsilon. Okay. So how should this equivalent circuit be? So I want you to try to calculate the capacitance. I think it should be quite straightforward. So for in this case, yeah. Uh, let's uh, I will like you to try in 10 minutes time. Yeah. So in 10 minutes time, I will write down the answer. So please try out. Okay, so by looking at the configuration, so the equivalent capacitance circuit should be uh, at one side is a series capacitance, and the other side is I mean, this side here will be parallel with the other capacitance. So let's say the capacitance for, let's say this 1, this 2, and this 3. So C1, C2, and C3. Okay. So C1 is equals to um, epsilon naught times the area. So this is half of the area. Okay, half of the area. So it should be 5 times 10 to the power of negative 4. Yeah. So cm square. So 10 to the power of negative 4 divided by the thickness. The thickness here is 2 mm. So half of it is 1 mm. So we have 0.5 epsilon naught. Then, sorry, excuse me. Then C2, again we have 6 epsilon naught. So this is the permittivity, the total permittivity, times 5 times 10 to the power of negative 4, the area, the occupied area, divided by 1 times 10 to the power of negative 3. So just now this is 0.5, 0.5 times 6 is 3 epsilon naught. And then C3 is epsilon, oops, epsilon naught times the area. The again is 5 times 10 to the power of negative 4, but the thickness now will be 2 mm. So it's 0.25 epsilon naught. Okay, so 5 divided by 2 is 0.25. I mean, it's 2.5. So 2.5 times 10 to the power of negative 1 and is 0.25. So in series, so first we will calculate the capacitor in series first. So the capacitor in series. So let's say I label the total capacitance in series C12. I just label it C12, C1 plus C2. That means 1 over C1 plus 1 over C2 inverse, yeah, the total capacitance. Um, so inverse, that means C1 C2 over C1 plus C2, right? So 0.5 multiply 3 is 1.5 epsilon naught square. C1 plus C2 is 3 plus 0.5, so 3.5 epsilon. So 1.5 over, okay, let's calculate this. 1.5 divided by 3.5 is 0.4287 epsilon naught. Yeah. So added with this in parallel. So C1, I mean, added with C3. So now this, the total capacitance of C1 and C2, now connected in parallel with C3. So therefore, the total capacitance. So C total is C12 plus C3. So 0.4287 plus 0.25. So it's 0.6786 epsilon naught. Yeah. So we multiply epsilon naught into this number. So epsilon naught we will use epsilon naught as 1 over 36 pi times 10 to the power of negative 9. So use this number, use this value here, multiply with 0.6786. So you get 6. It's actually 6 lah. Yeah, 6 picofarad. The calculation I get is 5.99998 times 10 to the power of negative 9, negative 12. Yeah. So yeah, so it's 6 picofarad. So that's it, actually. So no more. I think that's the end of this chapter. So the subsequent chapter we will deal with magnetostatic field. So before we end today's sessions, okay, uh, anything that you would like to clarify? Okay. So if no questions, then we will end our sessions today. All right. Thank you, everyone.